Okay, so we're given this function of u. Okay, but u in turn is a function of x, right? So what we're really trying to do, if we call this whole thing, let's just call it y so we can make it easy to keep track of. Oops, frozen. Okay, so if I set this whole thing equal to y, then what we're really trying to find here is we're trying to find dy dx when x equals 0, right?
Yeah.
Okay, so we're trying to find dy dx when x is 0. All right, so let's do that. dy dx now. We've got, to use the chain rule here, we've really got two layers, don't we?
Yeah.
Right? We've got a function of u, and then u is a function of x, right? So how could we write the chain rule here in a way, let's use this notation. So we're going to be able to write, we're going to be able to get dy dx even though we're given f as a function of u. So what are we going to get? dy dx equals,
dy dx equals f prime of u.
okay, f prime of u, same thing as dy du, right? Okay. So we could do it like this. We could say it's f prime of u times u prime of x maybe, right? But we've been sort of talking about it using the ratio form. So dy dx equals dy du times du dx, okay. Well, let's calculate up here. We're given, here is y as a function of u, right? So what is then what's dy du?
2u squared plus 10.
Okay, so how am I going to differentiate this? We have to use quotient rule, aren't I? So we're going to have the bottom times 2, derivative of the top, right? Minus
2u times 2u.
Everybody agree?
Yeah.
Minus the top times the derivative of the bottom, Riley, which is 2u, right? Right, Riley? Right? Okay. Divided by
U squared plus 5 squared.
Good. So there's dy du, right?
That's where I got it wrong.
Okay. So let's look at this part. So now we've got u equals a function of x. So let's calculate du dx.
8x plus 5. Oh.
Right?
No, wait.
All I did was just differentiate this, right? With respect to x.
The derivative of that. Oh, okay.
Okay, there's u as a function of x, so we differentiate u with respect to x. And so what we end up with then is just the product of this and this, right? Now let's not go any further than that for a second. Let's kind of talk about our strategy here. So we end up with equals u squared plus 5 times 2 minus, what's that, just 4u squared? Over u squared plus 5 squared times
8x plus 5.
Okay, so they're not asking us here for the simplified derivative, are they?
No.
All they want to know is what's the value of the derivative at 0. So they're asking for a specific value. Therefore, we don't need to do all that extra work to, for example, substitute u's into this, right? No need. All we really need to know is when x is 0, what's the value of u, right? Does that make sense? Isn't that easier, right? When x is 0, wouldn't it be easier to just substitute in, to just find out, well, here's u, right? u is g of x. So would you agree that then when x equals 0, u equals what? 3. Isn't that a lot easier to just establish the value of u when x equals 0 and plug in 3 for u and 0 for x to find the derivative? A lot easier, right? How do I know? Because if I plug 0 in for x, I get 4 times 0 squared plus 5 times 0 plus 3.
Okay.
Right? And so this makes our answer then, we just get, see that was 3, so I get 2 times 3 squared plus 9 is, what, 14? Minus 4 times 9 over 14 squared times 5. So that's my answer.
Huh?
Can't you just simplify the first one?
What do you mean?
Can you simplify the quotient one and then
Oh, I could, sure.
substitute in 5?
Yeah, I could. Yeah, I could, I absolutely could. I could distribute the 2 and simplify. I could.
Wait, time out.
Yeah.
Can't you just not even go to that step and just plug it in at the top? Where we have the very first equation?
What do you mean? Right, right here?
No, up. With the
All the
pink
way,
and the black.
dy over
That
dt.
one? Can't you simplify that one and then substitute in 5?
Substitute in 5. You mean substitute in 3?
Yeah, can you just put in 3 there?
If you substitute in 5, you get the right answer.
See?
Okay, substitute 5 for, what do you mean substitute 5 for what?
5, because you took the derivative of the u equation,
Right.
and if you substitute x to the derivative of that, you get 5.
Oh, that, okay, yeah, which is what we're gonna get. You mean right here? Oh, yeah, we did. That's 5, right there. Same thing, right? That's what you're saying.
Yeah.
Because really, this is just, you're saying that the value of this is 5, which is what we got.
Yeah.
Yeah, okay. You had a question,
Okay,
Lance?
my question was, at the top we have it in the pink and the green and the black. Can
Mhm.
you just put the 3 in up there?
Sure, that's the very same thing. I didn't change anything.
Okay, so then you don't.
That's just that.
Okay, so it's.
All I did was put the 2 out front and I just multiplied that. I mean, that was it. Okay, so, question?
So if they hadn't given us, like u equals g of x, they didn't give us that, would we have just been left with the pink and green one times, d du dx?
Yeah, times a u prime or a du dx, you're right. And we couldn't have gotten a numerical answer then. Right, it would have been impossible. Does this make sense though?
Yeah.
So if we, I mean, I guess we could trust here that if we do this, what are we gonna get? 28 minus 36 is negative 8
Over 196.
over 196 times 5, so negative.
10 times that.
So 8 that must go into that. I think 8 goes into that. We're gonna, 4 goes into that. So this is gonna reduce to a 2, and that's gonna be a 49, yeah. So we're gonna get negative 10 49s. That's it. Okay? Make sense? Okay? Do this. So for a spherical balloon, I want you to find the VDR. So I guess we need to know real quick, what's the formula for the volume of a sphere?
4 pi, 4/3 pi r squared.
Yep, that's it. Okay, so please find for me the rate of change of the volume of the balloon with respect to radius, because that's what dVdr is, right? Yeah, should be pretty easy.
Mr. O'Hare, we have questions like this on the test.
Not on this test, but on the one coming about 2 weeks later, you will, yeah.
2 weeks?
Yeah, ish.
Is it just gonna go up to the chain rule on this test?
Yeah, yep, just go with the chain rule.
How far back, are we gonna have like stuff on development?
Yeah, not much though, not much.
Is
You
it
might wanna
taking
just review
mostly
it.
the chain rule?
Yep, just the chain rule.
Are there gonna be 2 tests?
I don't know that yet. I think probably two parts to it.
Are there gonna be like 10 questions?
Yeah, it'll probably be something that's gonna take you more than a day to do, I would think. But I'll do it in 2 parts, so maybe you only have to redo 1 part.
Yeah.
I think it's better for you to do it that way, honestly, because then it's not one big, you know what I mean?
I was just thinking it's a 10 question test and you miss one, then you get like 90. So I was thinking like.
Yeah, yeah, I get that. But there'll be partial credit on it too, though. It will get partial credit. Okay, so here we go. Let's have a look. Okay, so what do we get? Okay, so for this part, let's look at part 1 real quick first. So part 1. What's dVdr?
4 pi r squared.
Good. So interpret that for me. What's that tell you? What's that tell me? The rate of change of the volume with respect to the radius is proportional to. Okay, well, so 4 pi is a constant, so it would say it's proportional to. So the rate of change of volume with respect to radius is proportional to r squared, right? Right? Because does that make sense? Because if I multiply something by a constant, that just means it's proportional to that quantity, right? Okay, that's interesting because that tells us, and this makes sense, doesn't it? If I double the radius of the balloon, what am I doing to the volume then?
Exponentially.
Well, I'm increasing it by a factor of what? By a factor of 4, right? Because the rate of change of the volume is proportional to r squared. It's multiplied by some constant, but the constant's going to be there all the time, right? No matter what the value of r is. If I double the radius, though, wouldn't you agree that doubling the radius and then squaring it is increasing it by a factor of 4? Right? Does that make sense? Because wouldn't you agree that 2r quantity squared is 4r?
Yeah.
Okay, so that tells us something. That tells us that as the balloon gets bigger, any increase in radius is getting us more and more volume as the radius increases, right? Okay, makes sense, doesn't it? Okay, let's go ahead and evaluate this at r equals 10. So at r equals 10, dVdr would just equal, what, 4 times pi times 10 squared?
Yeah.
So
Why would that not-
400 pi.
Why would that one you put in 2r to the square equals 4, why would it not be 4r squared?
Oh, r squared, you're right, sorry, r squared. Yep.
So it was simple.
What's that? It was pretty simple, yeah, no big deal. Okay, let's do it again. Same problem, same problem. Different derivative though, right?
What do you mean?
Why
Okay.
would you
Now I'm asking you something different. Same spherical balloon, but now I'm asking you for dV dt, the rate of change of the volume with respect to time. Does something sound a little strange about this?
Yes. Yeah, there's no equation with time in it.
You're right, there isn't, right? And so, does it sound like maybe that's not gonna be you don't have enough information to give a specific answer? Doesn't it sound that way? You're right, you don't. But we can still do the calculus though. Oh, boo. So let's find dv dt. Okay, we can do this one together, that's fine. So what do we do first?
Find the derivative.
Okay, find the derivative. Really what I've got here is I've got some constant, 4/3 pi, which I just always leave out front, right? Times r cubed. Now what's the derivative of r cubed with respect to t though? How many layers are there?
2.
There are two. There are two, aren't there? Because I've got the derivative of something cubed, and then
Times time.
when I pull away my hand, see what's behind it, it's an r, it's not a t. So dr dt is another link in the chain, isn't it?
Yes.
Right? So would you agree then, when I do the first part, I'm just gonna get the 3 cancels the 3 on the bottom, right? So just like before, the first layer here gives us 4 pi
R.
r
Oh,
squared.
and then you just time that by dRdt?
Yeah,
Oh, dRdt.
yeah. I've got to multiply that though by dr dt. Now, before we go any further, I want you to just ponder this for a second, because this is really cool, what we just got there. This tells us something important. It tells us that the rate of change of the volume actually depends on 2 things, doesn't it? What's one thing that it depends on? The radius, which makes sense, doesn't it? Because we found in the previous example we looked at that the radius determines, it has a profound impact on how fast the volume is increasing, right? Okay? But it depends on something else too. It also depends on that. Now somebody say that as a rate, please.
Radius of radius.
The rate of change of radius with respect to time. So we need to know 2 things here. If I want to know how fast the volume is increasing, I need to know A, what's the radius, and B, how fast is the radius changing with time, right? Make sense? Well, what if I gave you that stuff? What if I told you that the radius was 10 and the time was, hang on, and we need more than that. I need you to know that dr dt, that's what I meant to give you, not that. dr dt equals 4, let's say. Makes it a little different, but
That's a lot easier.
a lot easier, right? And so really all I'm doing then is I'm just plugging those values in, right?
Plug in the 4
No, you
R.
couldn't, because nobody told us up here how fast the radius was changing, right?
We don't.
And we need to know that. We need to know how fast the radius is changing.
So now we can just do 4 and we're golden.
Right. Right.
So what do we do? We plug in the 10 for R.
So you'd plug in the 10 for R, and you'd plug in the 4 for dr dt, and you'd have your answer, right?
You get 1600 pi.
Yeah.
Is that how it's like just
Okay, honestly, what I just did, I kind of slipped in a more advanced problem. This is actually, with a little tweaking, this is gonna be the kind of stuff we're gonna do after this next test. This is really the great stuff. But I think it illustrates the point pretty well.
Yeah.
What I wanted to show you here is, I think it illustrates really what the chain rule does for us, right? What did the chain rule do? Well, the chain rule, if we differentiated volume with respect to time, we had to get that extra layer, right? The earlier derivative we took on the last problem, that was a 1-layer derivative, wasn't it? Right, because we were differentiating volume with respect to radius, and we had volume as a function of radius, right? So we've got 1 layer for the something squared, and then inside that, I don't have another layer because dr is just 1, right? That's not a layer. But on this one, I added an extra layer. I had to include at the end this dr dt, because I was trying to find the rate of change of r with respect to a different variable. And so that is a rate. That's a rate, that counts. That's something different than just 1, right? Okay, I think you're good. I mean, I really do. I think this is just a little glimpse of why, what do we do with this, right? We're gonna be doing what we're gonna be doing here pretty shortly is pretty cool. We're gonna be doing things like saying, if we're adding volume to a balloon at a rate of 1 cubic foot per minute, then how fast is the radius changing when the radius is 10 centimeters? Okay, we'll be able to, that's kind of a cool question to be able to answer. We'll be able to tell how fast it's changing in terms of centimeters per second, how fast is the radius increasing. So that's where we're going with this. This is just kind of this is just the precursor of that is all. Just getting the skills that allow you to do that, okay? All right, that was a little shorter than I thought. I guess we do have a little time.